Hi everyone, welcome back to week 9 of our Biochem Weekly Reviews. So this is kind of one of the in-between weeks. You haven't started a really big unit yet, but you just finished a kind of bigger unit. So the chapter that you covered yesterday and the one you're covering tomorrow are more an introduction to the sections that you're about to start. So this is a bit of an easier week, but it's really important to get this stuff down for future PowerPoints or for future chapters. So this first question comes kind of from last week's review. I added it, but it was the very last question, and I don't know that it was covered super well. So I want to talk about it again just to make sure. So the idea is our metabolic pathways are very, very regulated, and here's why. Okay, your catabolic pathway and your anabolic pathway are almost identical, with the exception of maybe 1 or 2 enzymes. Okay. And so, because of that, if I want, for example, to form my product, if that's my goal, then I have to turn E3 on and E6 off, okay? Then let equilibrium, let whatever spontaneous reactions I have do the rest and push that reaction forward. On the other hand, if I don't want to get my product, if I have too much product and now I want to switch back and form my A, which is just my starting reactant, well, now I have to switch gears and I have to turn off E3, which was on before, and I have to turn on E6 to let that happen, okay? And so because our metabolic pathways use so many of the same enzymes and use so many of the same reactions just in reverse, we have to be very, very regulated so that we're not forming, some product and some starting material at the same time when we really want one or the other. Okay. Another thing to point out here is the reactions that are regulated tend to have different enzymes, which means that these reactions can be forward or reverse. In other words, their delta G's are near 0. They could be spontaneous or non-spontaneous, and they don't really need a ton of energy to go one way or the other, because they could go either way. Because of that, these reactions, the reactions, forward and reverse reactions catalyzed by E3 and E6, tend to be very spontaneous in one direction, and not so spontaneous in the other. And so we need a different enzyme to catalyze the reverse reaction. But because we have a different enzyme to catalyze that reaction, that opens the door and allows us to also regulate that reaction. Okay. So that is one of the biggest topics that we're going to be discussing over the next several weeks and really through the end of the semester. The idea that glycolysis and gluconeogenesis follow this pathway, or follow the same idea. In fact, I believe they have 7 enzymes in common. The fact that glycogenesis, or the formation of glycogen, and glycogenolysis, the breakdown of glycogen, follow the same pathway, the same idea with their pathways. This is something that's going to keep coming up again and again, especially in this unit, for which you're going to take the exam in about 2 weeks, because both glycogen and gluconeogenesis are on this exam. Okay? So shifting gears to the next section that I want to talk about is, what role does compartmentalization play in metabolism? So compartmentalization is, I have 2 answers for this, and I'd like to discuss them both in a lot of depth. The compartmentalization is exactly like we see down here in this diagram, putting all the hydrogen on one side and then having some bilayer or some barrier and a couple of channels, and then getting energy out of that. So that's one of the big reasons that we have compartmentalization. A lot of our reactions, or I should say, a lot of times we call things like NADH and NADPH reducing power. what does that mean? How is it reducing power? And the reason is, when these guys get oxidized, they release protons and electrons, I should say. But the protons are what we're specifically talking about here, because these protons get released onto one side of this barrier and create a concentration gradient. As they go down this gradient, they give us what's called the proton motive force. Proton motive force. Okay. This proton motive force in this specific example, which we're going to learn about in the 4th unit with the electron transport chain, it can spin ATP synthase, which helps us produce ATP. In other examples, the proton motive force can do something a little bit more directly, but in general, this is energy, or potential energy, that we have available to us because we have these two reduced elements or reduced molecules that give us power when they get oxidized. Okay. Now there's another role that compartmentalization plays. This is a diagram that I grabbed directly from your book and your slides, and I want to talk specifically about pyruvate in this diagram. So pyruvate, as I'm hoping your professors have mentioned, and it's something that I think almost every professor mentions, is the most connected metabolite. In other words, on that huge map of all the metabolic pathways together, where there's a million different things on there, pyruvate is connected to a ton of those pathways. Okay, so how is pyruvate going to know whether it needs to do, for example, anaerobic respiration, whether it needs to go into the citric acid cycle, whether it needs to be involved in any of the other dozen reactions that it can be involved in? Compartmentalization helps with that too. Okay, the citric acid cycle is compartmentalized, also called the TCA for the tricarboxylic acid cycle. I prefer saying TCA, so I'm probably going to be calling it that for future reference. This TCA cycle is compartmentalized to the mitochondria. So if pyruvate never enters the mitochondria, then it's never going to undergo the citric acid cycle. So on the other hand, if pyruvate maybe goes into, in a plant cell, a chloroplast, maybe it has a different reaction that it can undergo. If it goes into the endoplasmic reticulum, it can have a different reaction. And so compartmentalization, specifically compartmentalization of the enzymes and just the general other things you need for these reactions, not just the starting material. So compartmentalizing the enzymes can help kind of figure out where we need to go and what we need to do. Compartmentalizing enzymes gives a little bit of organization to our metabolic pathway. Organization to metabolism. Okay. All right. So these are kind of the two biggest points that I wanted to discuss with respect to the metabolism chapter that you covered yesterday. There is a little bit more to it that we discussed last week, just generally about the basic ideas of catabolism and anabolism, some of the vocab. These are the two that I think are the most important for the future chapters that we're going to be discussing. So I wanted to cover them. So tomorrow, you guys are going to be discussing carbohydrates, okay? And carbohydrates are really, again, just an introduction so that you can cover glycolysis and the future pathways associated with glycolysis without rushing or like with having the same background information. But I do want to discuss this carbohydrate chapter in a little bit of depth just because there are a couple of sneaky exam questions that you can be asked about it. So the first question is, what is the difference between an aldose and a ketose? Okay. Now, when we name sugars, aldoses and ketoses are very common kind of classifications of sugars. Okay. Aldoses can have some number of carbons. They can have, between 3 and 7 for a monosaccharide. Ketoses can have the same. That really doesn't tell them apart. Number of monosaccharides, so this would be for something like an oligosaccharide or a polysaccharide. The polysaccharides can be made up of both aldoses and ketoses. This doesn't really help. L conformation and D conformation. Well, L and D correspond to the conformation of an aldose or the conformation of a ketose. Not really relevant here. Finally, nitrogen, not really relevant. The difference, as I'm sure many of you guessed from your background in organic chemistry, is the carbonyl functional group. Aldoses have, exactly as their name would suggest, aldehydes for their carbonyl, and ketoses have ketones. Okay. As a side note, we know that our carbohydrate will have some kind of carbonyl because their formula is CHON, and because of this, and if we calculate out the degree of unsaturation, we're going to get 1 degree of unsaturation caused by a carbonyl. So these are a couple of examples of glyceraldehyde and dihydroxyacetone. So glyceraldehyde is a great example of an aldose. In fact, it's highlighted. You have an aldehyde here, or on the other one, which makes it an aldose. When we look at dihydroxyacetone, it's got a ketone. Makes sense. Okay, so this is the difference between an aldose and a ketose. It's basically just the position of the carbonyl, because if carbonyl is in the first or the last position, it has to have a hydrogen with it. It has to be an aldose. If it's in the middle, it's got to be a ketose. Okay. And I'm not pausing for questions, but if you have any questions, please feel free to type them in the chat, and I will do my best to get to them. So, how do we number them? This is a great question that we have to figure out how to answer. So, numbering, in other words, glucose that I picked and fructose are both 6 carbon chains. How do we know which one is number 1, which is number 6? So aldoses are very easy. Okay, with aldoses, we start at the aldehyde. Since the aldehyde is on a terminal end, and in this case it's this one, it's 1, 2, 3, 4, 5, 6. Done. Easy. Ketoses are fairly similar. Can be a little bit more confusing because you start closest to the ketone. You start at the end closest to the ketone. So our ketone is right here. That's closest to this top. So it's going to be 1, 2, 3, 4, 5, and 6. Okay. The numbering itself doesn't tend to be really complicated. I have seen a lot of students mess it up just because ketones or ketoses can be a little bit weird. Okay. So I've discussed L and D isomers a few times in the multiple choice question we just talked about. Down here they're labeled L and D. They're both labeled D in this case, but let's talk about what that actually means. Okay, so drawing the L and D isomers of each. So I'm going to start up here because this has both of them. So the biggest difference that we see between the L-isomer and the D-isomer of glyceraldehyde, really the only difference, is on the side there's an OH in the D-isomer. On the left side, on the L-isomer, there's an H on the right side. And then on the left, you have the OH in the L-isomer and the H on the D-isomer. In other words, the way that I think of it is L-isomer has it on the left, and it is the OH. Okay, D-isomer has the OH on the right. Okay, and so when we look at these two, the glucose and the fructose, we see, and oh, I apologize for future reference. Glyceraldehyde is a strange example simply because there's only one chiral carbon, but when you have a longer chain in a carbohydrate, it's the very last chiral carbon. Okay, so carbon number 6 in both of these is a CH2OH, CH2OH, and then some functional group up here. Because this carbon has 2 hydrogens, it is not chiral. It is not considered for L or D. Okay, the one right above it, in the case of glucose, has the OH on the right. That makes it the D-isomer. In the case of fructose, once again, the glucose on the right makes it the D-isomer. Okay. Now, the reason that the next question is here, the reason that I ask draw the L and D isomers, is because it's not just the carbon at the bottom. Okay, and what I mean by that is if I were to draw L-glucose, so L-glucose isn't just this one swapped around. So it's not just HOCH and everything else is the same. When we discuss L and D isomers, they're really not isomers, they're enantiomers. So thinking back all the way to OChem 1, an enantiomer and an enantiomer, sorry, it's hard to differentiate that, is a non-superimposable mirror image. In other words, every chiral center flips. Okay? So before you guys get flashbacks to OChem and having to do chirality for every single chiral center, it's a lot easier in biochem. And the reason is that the chiral centers are really just, let's use green. Any carbon that has both an OH and an H is going to be chiral. And the way that we flip it is we just swap those two around. So I'm going to go ahead and draw the D-isomer of glucose down below where I have a little bit more space. So I'm just going to repeat this, keeping in mind that the OH needs to be on the right, then the left, then the right, then the right, with the 4 chiral carbons. So it's going to be CHO, HCOH, CHOH, HCOH, HCOH, and then CH2OH. So let's double check to make sure I got that right. It's right, left, right, 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 left, right. Okay, terrific. So this is D-glucose. Glucose. L-glucose is going to be the switching of every chiral center. So trying to give myself a little bit more space so I don't run out of room like below. This first one is going to be swapped. Excuse me, that was weird. The second one is also going to be swapped. So it's going to look like that. The third one also swapped. And this one will also be swapped. HCOH. And then the bottom one, nothing changes since it's not even chiral. Okay? So, in other words, L and D, every chiral center switches. And I really want to emphasize that because I think it's something that a lot of students make the mistake of just looking at the very last one. Okay? For fructose, I'm just going to use this area right here because I don't really have much space elsewhere. So with fructose, we have to ask ourselves, is this chiral? No, okay, it'll stay the same. This isn't chiral, and this isn't chiral. So fructose only has these 3 chiral centers. So I'm going to draw CH2OH the same. I'm going to draw C double bonded to the oxygen the same. And this one that's highlighted in yellow is going to be flipped. The one that doesn't have a highlight in the middle, carbon number 4, is going to be flipped. So it'll look like that. And carbon number 5 will be flipped. Okay. So some of you guys might be asking, and this is a common question, I asked the same question myself, what happens if maybe I forget to flip number 4, or I flip only number 4 and don't flip the others or something like that? The short answer is you've made an entirely different sugar. So, and this is something you'll see in your slides probably tomorrow. Every single sugar has a slight, or every single sugar that is named has a slight different chirality. So mannose is another aldose. Glucose, 6 carbons. It seems like it would be the exact same, but whereas glucose has this pattern of right, left, right, right, for example, mannose has a slightly different one, okay? And so it's really important to make sure to understand you have to flip every single chiral center, because otherwise you're making an entirely different sugar, okay? The next question that I'm sure everyone's going to ask, do we have to memorize all of these? The short answer is it really depends. Some professors will encourage you and require you to memorize certain ones. Some professors will say, only do glucose and maybe fructose. I would strongly encourage you to ask your professor because I can't give you that answer very easily. Okay? So, that's L and D isomers. Does anyone have any questions about sugars with respect to their L and D isomers? Or really with anything that we've discussed so far? I'm going to pause for a moment. Oh. So far we've been talking a lot about that line angle formula. That's all we've been dealing with. But sugars can also be drawn in what's called a Hayworth projection. Hayworth projections are the chair form, I should say. I think that's the most appropriate way to call it that. They're this, basically, a six-membered ring formed by glucose. And what happens, or I should say the 5 or 6-membered ring formed by a sugar. It's not always 5, it's not always 6. So I'm going to go ahead and copy this image, because I did not realize I would be taking so much space with it. And I'm going to discuss how we get to a Hayworth projection. Okay? Effectively, what's going to happen is remembering that our carbonyl, in general, is partially positive. That makes it an electrophile. Okay? The oxygen of carbon number 5, or of your chiral carbon in general, of your last chiral carbon, is going to come in and attack that carbon. Okay? And so what you're going to get is you're going to get a 6-membered ring of 1, 2, 3, 4, 5 carbons and an oxygen. Your oxygen is the 6th member of the ring. So when we scroll down to here, we see 1, 2, 3, 4, 5 carbons and an oxygen. And then the 6th carbon is kind of hanging right up here. And that's, I should highlight them. The 6th carbon is this, and it's this. Okay? So when we attack our electrophilic carbonyl, all the way back to OChem, our CO, this has a hydrogen attached, this is going to come and form a negative charge, which will eventually be protonated. And so ultimately what we'll get out of this is the 2 bonds that it already has, one to a carbon and one to the oxygen that it just formed, an OH, which is this one, and the hydrogen that it already has. Okay? So these 2 are in the ring. It's a fixed structure within that ring. The other 2 have a little bit of flexibility, and this is where the idea of alpha and beta glucose come in. So alpha glucose is glucose where what was the aldose carbon, what is carbon number 1, has the OH pointed down. Beta glucose has the OH pointed up. Okay? And the reason that this is important is because it affects how bonds are made. Okay? So when I go to bond, for example, 2 units of glucose together, the way that they generally attach is 1,4. Okay? 1,4. So if I have, and I'm just going to draw a little bit of this glucose molecule, so OH and then the rest of it this way. If I have a hydrogen here and an OH here, well, this is a little bit easier. The OHs are pointed right next to each other. These 2 are what form the bond. It's called a glycosidic bond. This bond, the alpha bond as it's called, is generally drawn, I should say, like this. And then this is the rest of the glucose. Or these are the 2 glucoses. So this is position number 1 of this glucose, this is position number 4 of this one. Okay. On the other hand, with beta glucose, and I'm going to use this as the left side. So beta glucose is going to attach to another glucose, and when it does, well, these are the 2 that have to react. So when they do, and this is an alpha glycosidic bond. I apologize, bond. The beta glycosidic bond looks something like, let's go that way, like that. Okay. It's not really a question of what's more stable, what's less stable. It's just because these bonds are different, we have to figure out why they're different. And the reason that they're different is because of this idea that alpha glucose is one way and beta glucose is the other. Okay? This is a concept that I think a lot of people get confused. It's not overly complicated, but it is something that can be tricky. Okay. So number 7. I kind of spoiled this, but I want to make sure that you guys are following along. Formation of a glycosidic bond, so one of these, releases what waste product? If you'd like to go ahead and type your answer into the chat, we can talk about it. Oh, me to it. Hey, perfect. Yeah, it releases water. Because, scrolling back up to here, when these go to react, our end result is one oxygen keeping them together. So this hydrogen and this OH leave as water. This oxygen keeps them together. Okay? Or I should say one of the oxygens. It's not specific as to which is kept and which isn't. So it is in this case, it's a dehydration. The reverse, so the breaking of that bond would be a yes, it is a condensation. I'm sorry, I had that backwards. Good question. So it is a condensation or a dehydration. Both are acceptable. Condensation, dehydration. So I'd love to ask if you guys remember what class of enzyme breaks this kind of, catalyzes this kind of reaction. I don't know that anyone will remember, so I'm not going to worry about it too much. Okay, so maybe someone does. Hydrolase, yeah, good. Okay, just wanted to make sure. Okay, so what form is a naturally occurring molecule of glucose most likely to take? So we've talked about D and L before. We never talked about which is more stable. Now there's these weird words, Pyrranose and Furanose. Okay, Pyrranose, and it's a little bit more complicated. It's a little simpler than it sounds like. This is just a 6-membered ring. Furanose, 5-member ring. 5-member ring. Right? Just based on that, well, we just talked about glucose up here. It's going to be a Pyrranose. Okay? So we can go ahead and say these guys are going to be wrong. So now between a D-Pyrranose and an L-Pyrranose, this is where the idea of naturally occurring molecule comes in. So for some reason, we're not sure exactly why, or at least I'm not sure exactly why, D-isomers of most of our sugars tend to be more common than, okay? So a naturally occurring molecule of glucose is most likely to be a D-Pyrranose. Can it be an L-Pyrranose? Yes. Can it be a Furanose? Yes. But it's most stable and it's most synthesized as a D-Pyrranose, okay? So is Pyrranose more stable than Furanose? Mostly because of the ring tension, yes. So remembering from, again, back to OChem, with hybridization, that is a terrible 6-member ring, I apologize. Let me redraw that. These bonds are about 120. If it's going to be flat on the page, it'll be sp2, which will give you 120 bond angles. Obviously, you can still take on chair or what are called the boat conformations with these, and so it's not always going to be flat, but there is a little bit more ring strain with anything that's not a 6-member ring. Okay? Good question. Really good question. So let's talk about Furanoses for a moment, because I think that we kind of gloss over them a lot because glucose doesn't make a Furanose. It's not really important, but fructose does. Okay, and I should say it's more common with something like fructose. So with fructose, the same thing is going to happen. Your last chiral carbon, in this case, this one, will go ahead and attack your carbonyl. But in this case, the carbonyl is in position 2 rather than position 1. So what that gives us is a 1, 2, 3, 4, 5-member ring. Okay, and that's generally drawn like this from carbon number 4. So I guess, and I don't remember the exact way we tend to name these. It might be backwards, so please fact check this before using this numbering. From carbon number 4, we have a CH2OH. And from carbon number 2, I believe I did that wrong. Oh, yes. From carbon number 1 of the ring, which is actually carbon number 2, I apologize, we have a CH2OH. Okay? And so furanose rings are common, but not always with 6-member aldolases. And since we use a lot of 6-member aldolases, we kind of get in the habit of ignoring furanoses, but they are fairly common, especially with something like fructose. Okay? Does that make sense? Okay, awesome. So now we're going to talk about glycosidic bonds. And I need to zoom out a little bit. So you have a disaccharide. A disaccharide, exactly like it sounds like, 2 sugars. So it's formed from the beta-glycosidic bond between a glucose and a galactose. And galactose, like we talked about with something like mannose, is another 6-member aldose with just different chiralities for some of its carbons. Okay, and it tells us specifically the first carbon of the glucose and the 4th of the galactose. So naming these is fairly easy. I only include it because it's easy to also mess up. So the first thing is, if you're told the type of bond it is, you need to have that in your answer. So A and D are wrong just because of that. Okay, doesn't matter what else they say. This tells us we have a beta-glycosidic bond. We need to show that some way. Okay. The next point is the first carbon of the glucose and the 4th of the galactose. So it's fairly intuitive. Glucose 1, galactose 4. Or galactose 1, glucose 4. The number that is closest to that sugar, so the first number corresponds to the first sugar, the second number corresponds to the second sugar. So because of this, we know it's B because it's glucose 1, beta, 4, galactose. Okay? So the naming is really important because it does help us get into the habit of understanding the bond itself. Okay. So if you give me glucose beta 1,4 galactose, if you have these 2 structures memorized, or if you have some reference sheet that you're allowed to cite, you can draw this bond. Okay, and that's something that's really important to understand. Okay. Right. So now getting into these larger structures. So now, rather than talking about a specific disaccharide, we'll talk about polysaccharides. And you might remember this from Intro to Bio 1 if you took it. But amylose and amylopectin are both polysaccharides. And they're both polysaccharides made up of alpha linkages, as you can see by all the choices. The key here is that they are slightly different. Okay? Amylose and amylopectin, they have to be different, right? Otherwise, they would be the same thing. So are they different in where they're linked? Is one of them branched and the other linear? What's going on here? And really, both C and D are very similar in that they both have, so amylose is branched in C because it's got 2 different linkages. Amylopectin would be linear because it's only got 1 type of linkage. Whereas in D, it's the exact opposite, where amylose would be linear and amylopectin would be branched. Does anyone remember anything about these 2 that might help, or should I just give away the answer? The answer to this one, okay, so the answer to this one is D. Amylose, so B is exactly backwards, if that helps. And I think it might because, C and D are really kind of long answers that are just kind of confusing. Amylose is linear, okay? Amylose is a linear chain. In other words, you're going to have this molecule of glucose attached to this molecule of glucose. And we can actually get more specific because they're alpha 1,4 linkages. We know that it'll look like that. Over and over and over again for as long as that chain is. Amylopectin has that too. Pectin also has those very same bonds. but amylopectin is also branched. So in addition to these bonds, and remembering that the numbering is 1, 2, 3, 4, 5, 6, amylopectin has alpha 1,6 attachments. So 6 and the first carbon of another glucose bind together. And this is an oxygen, these are oxygens that I forgot to label. Things like that. And so what you end up getting is amylose straight chain. Amylopectin will end up looking like that kind of. It depends. So that's, for the most part, yes. But for example, if you had a pattern of alpha 1,4, alpha 1,6, alpha 1,4, alpha 1,6, it's still a linear chain. It's still one single chain. It's not a branch chain. It's just got alternating bonds. What we see with amylopectin is the same glucose molecule has multiple bonds, and that's what makes it branched. Does that make sense? I know it's really kind of unintuitive. I just want to make sure. Okay. So unfortunately, most of your professors will never ask a question like this because it's too simple. Instead, they'll ask the very next question. What kind of glucosidase could be used to convert amylopectin to amylose? So, fun fact, they're asking the same thing. Okay? The glucosidase is exactly what you'd expect it to be. It breaks a glycosidic bond. Glycosidic bond. Okay? So, how would we convert amylopectin to amylose? Well, they both got alpha 1,4 linkages. We have to remove the alpha 1,6 linkage somehow. So amylopectin minus the alpha 1,6 linkages. And I don't want to call it equals because I'm sure there are some slight differences in terms of how long they could each be. But generally speaking, amylose is classified as alpha 1,4 linkages. Amylopectin is both alpha 1,4 and alpha 1,6. So because of that, the answer would be B, because we need a glucosidase to break alpha 1,6 linkages. Okay? That's kind of how they want you to start thinking about this next unit. Not just memorizing, but applying it and understanding what's going on. And this is definitely going to get more clear when we get into the glycolysis section, because with glycolysis, you're not just memorizing the steps, you need to understand how it's regulated, to understand the spontaneity of various reactions, kind of like we talked about in the first question today. Before I shift gears, do you have any questions about this idea with these polysaccharides? And there are more, by the way. There's a lot more polysaccharides in your PowerPoints. Amylose and amylopectin are almost always expected to be memorized. The others are somewhat professor dependent, so I figured I would just cover these two to make sure that it works for everyone. So the last the last kind of weird topic in this chapter, in chapter 7, I believe it is. Yeah, chapter 7, is gram-positive and gram-negative bacteria. And this is something that I'm sure you'll hear a lot in media, like, oh, it's gram-positive, gram-negative, but what does it actually mean? So I pulled these two images from your PowerPoints. And I want to kind of zoom out a little bit. Right there, that's good. Talk about it. So these are the cell walls, and these cell walls have, these various acids and these various molecules that kind of hold it together. And then between these kind of chains of NAM and NAG, you have a connection, right? Now, in gram-negative, this is that connection. In gram-positive, this is that connection. And that's really what it comes down to. That's the difference between the two, okay? So as I'm sure you see, I'm going to go ahead and delete that so that I can do this. The difference here is pentaglycine. So when you're linking your two, or I should say your series of like molecules in your cell wall, you use these various amino acids, and those amino acids connect to others. The connection in gram-positive cell walls uses a pentaglycine crosslink, and gram-negative, it doesn't. Okay, so this makes some more or less, it's called here, yeah, direct crosslink. So this makes some more or less affected by various tests, and so it's a really helpful way to identify a little bit of information about this, about the bacteria that we're dealing with. It's not a major topic. In fact, I've only seen maybe 2 exam questions about it in the past few years, but I thought I'd mention it just in case, because it is a topic that a lot of students kind of get confused on. Okay. And I'll say I got confused on it too. So that's kind of the major topics for chapter 7. I want to shift gears a little bit because once we start the glycolysis and gluconeogenesis units, we have to start going a bit quicker. So I wanted to include a little bit about glycolysis just so that we could talk about the reactions before we start going into a lot of detail next week. Before I do that, does anyone have any questions from either this week or last week, since last week was also about metabolism and was kind of introducing us to glucose? If we want to go over mechanisms, the models of regulation, things like that, this glycolysis unit is really to prepare us for next week's review. Sure, so let's go over the enzyme models. So the enzyme models, and I'm probably going to have to erase quite a lot since I wrote all over this, but the enzyme models, we're going to talk about the MWC and the Knf models. So this is a picture of the MWC model. And the MWC model is based pretty much on Le Chatelier's principle. So we have effectively the things that we look at with the MWC are this R0 and T0. And everything else afterwards is affecting that, but really the core of it is R0 and T0. R0 can bind to substrate. T0 cannot bind to substrate. Substrate, okay? So, thinking about this in terms of the equilibrium, when R0 binds to a substrate, and we're not going to get into activators just yet, but when it binds to a substrate, the concentration of R0 decreases. That's what this down arrow above represents. This one right here, we're just going to draw it again. As R0 decreases, Le Chatelier's principle tells us that the equilibrium will shift to compensate for that. And that decreases the concentration of T0. Okay? And so more R0 means more stuff can bind. Okay? This is also how activators work. Activators bind to R0 in a different site than the substrate that decreases the concentration of R0. In order to compensate, T0 concentration is decreased to make up for that and give us a little bit more R0. So what we end up getting is R0 and what's called R1A, which can also bind to substrate. And so because of just looking at this left half, binding things to R0 increases the relaxed forms in general. So not just R0, but the total amount of R0 and R1 and the various types of R1s increases that overall concentration and increases binding. Okay. On the other hand, the tense form, which cannot bind to substrate, this is where inhibitors bind. So when I have an inhibitor bind to my T0, well, that decreases the T0 concentration. And as a result, my equilibrium shifts to the right. And I get less relaxed form in order to make up and get a little bit more of my tense form. Okay, does that make sense? Okay, awesome. So that's most of the concept of the MWC model. The next, and this is one that I think is a lot more confusing, to be honest, is the Knf model. So the Knf model, and I want to clear all this so that we can talk about it again, is based on the idea of conformational changes. So specifically, it relies on oligomers. So when you have this enzyme, that's some oligomer, the binding of the substrate to the first monomer changes the conformation of that monomer. Okay? That change in conformation changes the other monomer. So this could be something as simple as when and I'm just going to call these it's called M1 and M2 for monomer 1 and monomer 2. When M1 binds to my substrate, that makes it shift a little bit, or like it forces the negative charges to all point out to bind to my positively charged substrate. And when that happens, it changes how the M1 and M2 bind. And so M2 changes just a little bit. Okay? This change can be something as simple as they move around and that opens or closes the binding site a little bit more for substrate. So I think one of the reasons that I personally got confused with this is I was like, how does that change M2 at all? And it's not really changing it necessarily. It can, but it can also be as simple as just moving something around. Okay. And so now M2 is, and I'm just going to call it M2 star. Okay. So now it's talking about affinities. So basically what it's saying is if my new M2 binds to my substrate better than my old one, what I've done is called positive cooperativity. Why? Because the binding of the first substrate increases the affinity of my enzyme for the second substrate. Okay, does that make sense? It's really kind of weird, but I just want to make sure. So when my M2 goes to M2 star, that affects how it can bind to the substrate. Okay. However, let's say just for convenience, they move a little bit, they rotate, and the binding site is a little bit more open. Okay. So the binding site being exposed a little bit more means more substrate can bind. Are we okay with that? More substrate binds means M2 star is better than M2 at substrate binding. Therefore, my enzyme, the polymer, the oligomer in this case, shows positive cooperativity because the conformational change induced by the first binding increases subsequent binding. Are we okay with that? Okay. So now what if the opposite happens? So now instead of my binding site being a little bit more exposed, now it's covered a little bit more. And that's what this second thing is. And again, we're only looking at these parts. We don't really care about the S. So now if M2 had my exposed binding site and M2 star is with the binding site covered, then what I've just done is decrease my affinity for future substrates, and I just got to negative cooperativity. Does that make sense? Okay, so a great example of both models is hemoglobin. And we talk about hemoglobin a lot, and I have this drawing here. I'm not going to use this drawing, I'm going to draw it again. Hemoglobin shows aspects of both. So hemoglobin is 4 subunits, 2 alpha and 2 beta. And for convenience, I'm going to use circles, or I'm going to use blue and I'm going to use gray. So my blue will be my alpha subunits, and my gray will be my beta. Okay? And when they're in their square conformation, they're less able to bind than in what's called the circular conformation. And these aren't like form terms, it's just how a lot of your book and your slides like to cover things. So the binding of the first O2 is going to happen to an alpha subunit. Okay? So when it's bound, I'm just going to color it in to show that it's got something in it. So it binds. Okay. Oh, sorry, that's supposed to be in gray. Excuse me. So now this binding, what binding to the first oxygen does is your hemoglobin is effectively an iron in the middle with 4 rings around. Okay? When the first one binds, or before the first one binds, I should say. So when we're in this form right here, the porphyrin ring is flat. The iron is sticking up right above it. Okay? And it's something to do with the bonding. I don't know the exact details of why that happens, but the big thing here is once this happens, iron is able to return to the plane of the porphyrin ring. Porphyrin ring. Does that make sense? I just want to make sure that I'm like, that what I'm saying is actually logical. Okay, good. So what happens? That changes the conformation of the other alpha subunit. So now instead of a square, it's a circle. It doesn't have oxygen in it or anything, but it's a circle. Okay, so that means it's got increased affinity for oxygen. And our beta subunits are the same as they've always been. Okay. So now we bind to our next oxygen. Okay. So both of our alpha subunits are bound, both of our beta are empty. Sorry, I apologize it's taking so long. Okay. So what happens here is, and I'm going to continue it down on the next row. What happens here is with both alpha subunits bound, they rotate by about 15 degrees. I don't know the relevance of the number, it's just what's happening in real life. But they rotate about 15 degrees, and that, exactly like we just talked about, it opens the binding sites of the beta subunits. Okay? Rotates, opening, beta binding sites. Okay. So both of the alpha subunits are bound by O2, and when that happens, that causes that little conformational change, that rotation, that makes the beta subunits more, not more susceptible, but more, it increases their affinity for oxygen. That's what I want to say. Okay. So now instead of squares, we're going to draw them as circles. Okay. And once this happens, both of them can bind fairly quickly. I believe in real life it'll be subsequent, so it'll be a third and then a fourth. In this case, I'm just going to draw them both binding at once because nothing really changes between the bindings. So I want to talk about this with respect to the Knf and the MWC models, because this shows hemoglobin binding shows both models. So the binding, let me highlight this. And actually, I want to erase this highlighting. So the binding of the first subunit, the alpha subunit, to the oxygen induces a subsequent conformation change in another subunit. That is Knf. Okay, this is Knf cooperativity. Does it make sense? Why? Okay, awesome. So Knf cooperativity, that leads to the next binding. So now, and one of the things that I think I could do to kind of give away, if I drew this as a double arrow instead, this is MWC binding in green here. Or I should say this is MWC cooperativity. And the reason for that is because if we think of this as the tense state, T0, because that's effectively what it is, right? In this state, no more oxygen is, the oxygen has a very low affinity for these beta subunits as they are, until they transform into their relaxed state where there's a much higher affinity. Okay? So because this is kind of all together, that transition is not one at a time. Actually, that's it's really what we talked about as well a little bit last week, is that the Knf model is called the sequential model, the MWC is called concerted. Okay, so everything happening at once. Sorry. Yep. Both subunits are switching places at once. That's concerted. That's MWC. Whereas in this one, K and F, it's ordered. It's sequential. One, then another, then another. Okay, does that make sense? Okay, awesome. So that is as brief an overview as I could give about the two models. If you have any other questions, please feel free to ask them, but I think that's a pretty reasonable description. One thing we also discussed is K and V systems. So a K system, very briefly, by adding an activator, you increase the affinity by decreasing K of the enzyme for the substrate. By adding an inhibitor, you decrease the affinity, but V stays the same. On the other hand, in a V system, adding an activator increases the velocity, adding an inhibitor decreases the velocity, and K stays the same. That's the other thing with inhibitors. Those are the two, I think, major topics. Okay. So, if there are no other questions, and if there are, please ask. I'm going to go ahead and shift gears to glycolysis to prepare us for next week. Are you okay with that? Okay, awesome. So, glycolysis, generally speaking, is broken up into two phases. And you're going to learn about these two phases on separate days from what I've seen on your syllabi, just because it's easier to teach it that way. The first phase is called the priming phase. So I should say the point of glycolysis is two things. First, to give us a little bit of energy through ATP, and second, to make pyruvate to make a ton more energy. Okay, so pyruvate is, I don't want to call it potential energy because I know that has a meaning in physics, but it gives us potential to make energy. Okay, so phase one is priming. It's getting us ready. It's giving us all the energy we need to get there, so that in phase two we can rush through it. Okay, so the first step is very simple. We use an ATP to add a phosphate to our glucose. So now it's not just glucose, it's glucose 6-phosphate. Okay. The second step is exactly like we talked about. We're making a fumarate, a furanose, excuse me, making fructose. That's fructose 6-phosphate. Okay. So I want to pause for a moment and discuss the fact that we used ATP here, and in the next step we're going to be using ATP. Okay. If we remember, ATP, I think this was back in week 2, maybe week 3 that we discussed this. The delta G naught prime of ATP hydrolysis is somewhere around negative 13.5, negative 31 are the numbers that we get, kilojoules per mole. In other words, using ATP, or like having ATP hydrolysis as part of a reaction, is going to make it very, very spontaneous. Because it's very spontaneous, this is going to be one of those reactions that, going all the way back up to question 1 of this review, this is going to be one of those reactions that we need to use a different enzyme for if we're going to go backwards. Okay? And I want to try to keep adding a little bit of those facts just because I don't want everything to be so disconnected, because I think they are really connected. Okay? The next reaction of fructose adding 1,6-bisphosphate to it, once again, we're using an ATP. This is going to be very spontaneous. So the reason that I mention these is because when you learn gluconeogenesis in a week and a half or so, one of the biggest things about gluconeogenesis that you guys are going to need to know is which reactions are the same as glucose but backwards, and which reactions have to be completely different. So without having the steps memorized, we can kind of assume this first step, we're going to need to use a different reaction. The second step, pretty okay. It might be a little bit spontaneous, but it's not so much that it's insurmountable. A difference in concentration will get us there. The third reaction, that's going to be very spontaneous. Fourth reaction, we're not really using ATP, but it is cleaving, so we're not really sure. This one, This one is one I don't want to comment on because I know that cleavages are a little bit different and like bringing them together. But the point of the fourth reaction is to cleave into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. Really, we want glyceraldehyde 3-phosphate, so this fifth reaction of this triose phosphate isomerase is going to convert any DHAP into G3P. Okay? And then at the end, we're going to have 2 G3P. So from now on, the suffix that we're going to see is 2 all the time. We're going to have 2 G3P, we're going to have 2 NADH, we're going to have 2 ADP, we're going to have 2, 2, 2, 2, 2. Okay? So just double everything that happens in phase 2. Okay? And this phase is the phase where we get some energy out of it, and we get pyruvate, which gives us the potential to get even more energy. So, glyceraldehyde 3-phosphate dehydrogenase is going to go ahead and reduce, reduce NAD plus into NADH and oxidize G3P into 1,3-bisphosphoglycerate. Oxidize to what's called BPG. Okay. Now we're going to go back to kinases, which we talked about months ago. Kinases remove one of these phosphate groups. In this case, this one. Okay. When that happens, kinase is removed. You get 2 ATP out of it. So in the priming reactions, we spent 2 ATP. Now we just made that up. So if we stopped here, we would effectively be energy neutral, but with a little bit of reducing power because we did make some NADH. Not bad. Okay. The next reaction is going to be similar. I'm sorry, not similar. It's a mutase. Once again, pretty energetically, okay, it's just moving something around. Okay. The next reaction is called an enolase reaction. This enolase is really a dehydration. Dehydration. Okay. You're losing 2H2O. Nothing else is really changing. You get phosphoenol pyruvate out of there, and once again, we're making ATP. Okay. So the fact of the matter is, glycolysis is energy positive. We get energy from glycolysis. Okay. And out of it, we also get pyruvate, which means we could get more energy, and we get NADH, which again, we could get more energy. So glycolysis, what it effectively does is we use a little bit of energy to make up for that little bit of energy and have the potential to make even more energy later down the line. Okay. So a couple of things that I want to highlight here are not really here, but in general, are when you start learning the next few units, glycolysis, the TCA or the citric acid cycle, and the next few sections, one of the things you're going to be asking is, why do we care so much about glycolysis when we get so much more energy out of the TCA cycle? The short answer to that is speed. Okay? We talk a lot about kinetics in the first half of this class for a reason. Some reactions are faster than others. Some processes are faster than others. Glycolysis is fairly fast. That's why when we want to, run a marathon or something, a lot of people will eat a ton of carbs right before because you can burn that energy really quickly through glycolysis, get some energy, even if not a ton, out of it, and then start and use that energy right away. Digesting something larger, going through the entire TCA cycle, all of that can take a lot more time and can be, less favorable in terms of how soon you need the energy. Okay. The other things I want to mention are coming back to this ATP hydrolysis. Well, the reverse of ATP hydrolysis is ATP synthesis, right? ATP synth. On paper, this ATP synthesis is really unfavorable. Unfavorable. And yet it still happens. Okay? The question is, why does it still happen? So this is something that I don't want to answer right now because this gets kind of really deep into the weeds of the energy. This gets really deep into the weeds of kind of what's driving glycolysis. It's just something to think about as you're learning this reaction, right? As you're learning these next reactions. Again, pyruvate kinase, why does this reaction happen? happen, shouldn't it be unfavorable? Okay, so these are just some things to keep in mind for next week when you start learning glycolysis and when we start going into a lot of depth about it. Okay, that's all I have for today. I didn't want to do too much today because this is a really kind of introductory week in the middle of the two big units. So if you have questions, please feel free to ask them. Otherwise, that's really it for today. Okay, awesome. Have a great day. Thank you for coming.